Welcome to our explainer on the ultimate scientific detective story, the evolution of atomic theory. Today, we're diving into how a few brilliant minds completely flipped our understanding of the universe upside down. It's an incredible journey of pure human curiosity, where scientists had to piece together the absolute fundamental nature of reality without ever actually being able to see it.
To keep this complex history organized, we're going to break this mystery down into 6 quick chapters: the atomic mystery, smashing the plum pudding, the nuclear atom, Bohr's quantum leap, the hydrogen spectrum, and finally, where Bohr fell short.
All right, let's jump right into Chapter 1, the atomic mystery.
So here's the billion-dollar question, right? How on earth do we know what an atom looks like if we can't even see it? I mean, atoms are usually around 100 picometers across. To put that into perspective, that is a 10 billionth of a meter. They're completely invisible to the naked eye. So early scientists couldn't exactly just throw one under a microscope. They had to rely on indirect evidence in some seriously clever experiments to deduce what was going on inside.
As you can see on this timeline, for thousands of years, and formalized by John Dalton back in 1803, we thought atoms were just these solid, indestructible little spheres. But then, boom! Between 1897 and 1926, a rapid explosion of discoveries completely tore up the scientific rulebook in just 3 decades.
Which brings us to Chapter 2, smashing the plum pudding.
Okay, our first major curveball hits in 1897 when J.J. Thomson discovers the electron. Now, electrons are negatively charged, but atoms overall are neutral. So Thomson realizes there's got to be some positive charge in there balancing things out. He comes up with the plum pudding model. Picture a positively charged liquid-like blob, kind of like jelly, with negative electrons just floating around inside it, exactly like plums in a traditional British pudding.
Well, a few years later, Ernest Rutherford's team decides to test this out. They take these heavy, super-fast alpha particles and fire them at an ultra-thin sheet of gold foil. Now, based on Thomson's diffuse pudding idea, the prediction was that these heavy particles would just blast straight through that weak positive jelly with basically no deflection. But the actual observation? It was jaw-dropping. While most went through, some of those particles violently bounced right back.
Rutherford's reaction really tells you everything. He was so utterly shocked by these bouncing particles, he later said, "It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. I mean, wow." He instantly knew Thomson's plum pudding model was completely dead in the water. That positive charge couldn't possibly be a soft diffused pudding.
Just to appreciate how crazy this was, let's walk through the steps of this legendary experiment. Rutherford, working with Geiger and Marsden, sets up a radium source to shoot out alpha particles. They funnel them through a lead slit to make a tight beam, then blast that beam at the ultra-thin gold foil. To track the deflections, they literally sat in a pitch-black room for hours, meticulously counting microscopic flashes of light hitting a fluorescent screen. Talk about dedication, right?
Moving on to Chapter 3, the nuclear atom.
So those ricocheting alpha particles meant the atom's internal structure was something completely different. Rutherford drew 3 massive conclusions here. 1, since most particles flew straight through, the atom is actually mostly empty space. 2, because a few violently bounced back, all of that positive charge must be packed into a super-dense center. And 3, that center, which he called the nucleus, takes up a minuscule amount of volume compared to the whole atom.
So now we have this neat little planetary model, right? Electrons orbiting a nucleus like planets around the sun. Well, actually, classical physics totally ruins the party. The fatal flaw here is that classical mechanics dictates a negative electron orbiting a positive nucleus would constantly emit radiation, bleed off kinetic energy, and instantly spiral into the nucleus. Basically, the atom should collapse in a fraction of a second. But, well, you and I exist, so atoms obviously don't collapse.
Chapter 4, Bohr's quantum leap. Let's see how we save the atom.
In 1913, Niels Bohr steps up to the plate. He actually starts with classical mechanics, looking at the centrifugal force, the momentum of the electron trying to fling itself out, and balances it against the Coulombic attraction, which is the literal magnetic pull of the positive nucleus drawing it in. This derivation perfectly shows that mechanical tension, but Bohr knew this balancing act wasn't enough to stop the collapse. So he makes this brilliant,
totally radical assumption. He just straight up proposes that electrons exist in stationary states. These are fixed circular orbits with specific quantized energies. And the rule is, when an electron is sitting in one of these stable orbits, it somehow defies classical physics entirely and just doesn't emit radiation. Problem solved.
To keep these orbits organized, Bohr assigns them principal quantum numbers, or n. These are simply integers starting at 1 and moving outward. An electron can only live on one of these specific, stable levels, never floating in the space between them. And to jump from one to another, it has to absorb or release an exact specific packet of energy.
Chapter 5. The Hydrogen Spectrum. Time for the proof.
If this sounds like crazy abstract math to you, you're not alone, but it actually perfectly explained a real-world mystery. When you heat hydrogen gas, it emits light, but only in very specific colors called the Balmer series. Look at this data. Bohr's model nailed it. When an excited electron drops from orbit 3 down to orbit 2, it releases exactly 1.89 electron volts. That exact energy difference gives you a visible red photon. A drop from 4 to 2, you get aqua. 5 to 2, blue. Bohr's math matched reality perfectly. By using Rydberg's equation, scientists could literally predict the exact wavelength, frequency, and color of light a hydrogen atom would emit, purely based on where the electron started and ended. Imagine being a physicist in 1913 and predicting actual physical colors using just math. It was an absolute triumph for theoretical physics.
But as always, Chapter 6, where Bohr fell short.
The scientific method is all about breaking things to make them better. And Bohr's model? Well, it broke pretty fast. It was amazing for a simple atom like hydrogen, but the predictions totally failed the second you added more electrons. It couldn't explain the tiny hyperfine spectral lines. It completely failed to explain the Zeeman effect, where magnetic fields split those lines. And honestly, giving an electron an exact speed and location fundamentally violates the new Heisenberg uncertainty principle.
So physics had to evolve one more time. By the 1930s, the rigid planetary orbits of Bohr were totally tossed out. Thanks to the work of Schrödinger and others, we got the modern quantum mechanical model. Now, we understand that electrons don't run on circular tracks at all. They exist in these fuzzy, wave-like regions of probability around the nucleus, which we call the electron cloud.
And that brings us to the end of our explainer. It's an unbelievable journey, isn't it? From Dalton's solid spheres to Rutherford's dense nucleus, jumping through Bohr's quantum leaps, right into Schrödinger's probability clouds. We've completely mapped the invisible building blocks of the universe, but it really leaves us to wonder, what other unseen mysteries about the fundamental nature of reality are still out there, just waiting for us to find them? Thanks so much for joining us for this explainer, and keep staying curious.